That's true actually. I remember it. The normal. These are there for audit. No, think we are in a what is there? Yeah, there. Oh, right.
மேடம் சொல்லுங்க மேடம். வால்யூம் வேணா கம்மி பண்ணலாமா நார்மலா?
Yeah, just can you speak again?
Five by 3. So.
Yes.
Good morning, everybody. So it's my pleasure to introduce Professor Rohit Medal from University of Paris 6 and 7 together. So he's visiting us for about a month, and he will be giving a series of lectures on Eisenstein cycles and Drinfeld Manin conjecture. I think it repeats every week, right? And dates are given anyway, and the content as well as the scope of the course, I let him explain in detail.
Thank you, Perusatam. So I think it's working. First, it's a pleasure to be here, especially after the last 2 years where there were practically no international relations in person. So it's good to see people from colleagues from abroad, and I should thank the institute here and the Indo-French program actually for allowing my visit. So there will be several lectures I will give on a certain topic. An abstract has been distributed and it corresponds rather to what I will say at the seminar level. But today's lecture will be at a more basic level. I will speak about the Manin-Drinfeld theorem and how it is proved and why perhaps it is interesting and what it is connected to. So let's start. So let's start with this fundamental object, the modular group SL2 of Z. And we will be interested in a subgroup of finite index. Among those group of finite index, you have the congruent subgroup. So let n be an integer other than 1. You have the subgroup gamma of n are the set of elements in SL2 of Z, which are congruent to 1 mod n. There are two other families of subgroup of interest. Gamma 1 of n is ABCD such that well, I don't really need to call them ABCD. Gamma congruent to 1, 0, 0, 1 mod n, modulo n. And then you have gamma naught of n, which is a set of matrices which are congruent to upper triangular matrices modulo n. Okay, so gamma is a congruent subgroup if and only if there exists some n such that gamma contains gamma of n. So there is a fundamental dichotomy between congruent subgroups and non-congruent subgroups. So the theory for congruent subgroup is, well, more or less a classical theory of modular forms. And the theory for non-congruent subgroups, surprisingly, it's surprisingly general because it has to do with all algebraic curves over number fields. Yeah. Arithmetic algebraic curves over number fields. This connection here is due to Bailey's theorem that I will discuss another day, actually, not today. Today we will focus on the theory of congruent subgroups. And this is what the Manin-Drinfeld theorem is about. So, okay, we have the subgroup of finite index and SL2 of D acts, or even GL2 of Q, in fact. On the upper half plane. And also on P1 of Q by homographies. So what's the connection between the upper half plane and P1 of Q? In fact, the boundary of the plane this set of topology and you have to be slightly careful because H is a standard topology, and you have to say what is the neighborhood of Q. So the upper half plane is above this line, and here you have X in P1 of Q, and the neighborhood of X is simply a disk which is tangent like this to the real line at X. So that's a neighborhood of an element of P1 of Q. And if X happens to be infinity, then a neighborhood of infinity is a half plane, or rather a basis of neighborhood, is a half plane above an horizontal line. So this is how you get a topology on the upper half plane with P1 of Q. So those the boundary of those disks are called orocycles. All right, and now you can take the quotient of this space by gamma, if you like. So set and partial gamma is P1 of Q. It's and it's something of the segment surface. And by the theory of Riemann surface, it's an algebraic curve. And in fact, this algebraic curve is defined over a number field.
I may sit the French.
So Bailey's theorem says that you can get every algebraic curve over a number field in this way. It's surprising, and but in many different ways. So there is no canonical way
Indo-French collaboration
to have such a model for an algebraic curve over a number field. All right. Um, so il y a des jouets cœur, So I'll give two explicit descriptions of the Jacobian. So naively, the complex point. So it's an abelian variety. So if you are not familiar with abelian variety, it doesn't matter. Simply as a group, there is one description of the Jacobian. This is a set of divisors of degree 0 on X gamma modulo the divisors of meromorphic functions on X gamma. So those are the complex points of the Jacobian. I will give another description today after I've stated my theorem. All right. So, of course, you can actually take divisors of the on the set partial gamma. The element for gamma are basically equal to the curve. So you can look the divisor supporters on the cusp and see what they are actually in this Jacobian. And the theorem is the following. So if gamma is a congruent subgroup, then any divisor d of degree 0 supported on the cusp is torsion in the Jacobian. Well, the theorem is just 50 years old. In fact, so it's not a new theorem, but a basic theorem. So the story was Manin was already an established professor in Moscow at the time. So he published his paper and he had a seminar. And he published his paper where he does not actually quite prove this theorem, but sort of a very weak form of it if you project the Jacobian on elliptic curves. So this is what he proved. And if you look, and this paper was submitted, I think I have the date. Where is it? 10th of October 1971. And then there is a note in the paper. It says, added in proof, Drinfeld showed me that actually with this method you can prove this theorem. And the following years there is a paper by Drinfeld, and where actually he proves the theorem. If you look at the biography of Drinfeld, you realize that he was born on February 14, 1954. So meaning he was probably not even 18. And the proof of the very short paper on and I create this So I gave here the sort of algebraic description of the Jacobian. We need now to look at the analytic description. So let's, okay, no, I'm not going to describe the technique right now. I need to make a series of comments, in fact. Yes, perhaps it's good to have some background. And perhaps it's important to mention the Manin-Drinfeld conjecture. I don't know precisely the statement of the Manin-Drinfeld conjecture, but I suspect that when Manin formulated it, it has nothing to do with what he did on compounds. So if you take a image surface, space, and you take video, like that. X, such that the class of P minus P0 in the Jacobian is finite. So this conjecture has proved and has been proved many times, in fact. The story is that, so first of all, the conjecture says that the fact that a divisor is the class is torsion. I'm sorry, I forgot that. The set of points for which the class divisor P minus P0 is finite. And so it says that the fact that you have a divisor of the critical is finite is a result of ray difference. And so the next question is that if you have because that the difference is really so about so science counter to the Manin-Drinfeld. About the proof of the Manin-Drinfeld conjecture, the first proof is due to Raynaud. I believe in the early 1980s. I don't know exactly the right date, so let's say about something like that. And so, as I said, there has been then a series of other proofs. I'm not sure I know all of them. I suspect I don't know all of them. And based on different techniques, this is what is so interesting. So there is a proof by Mark Indri, or I think also in the 1980s, quite different from Renault's proof. And there is another proof by Robert Coleman based on periodic integrations. So Indri's proof is based on heights, I think. There is proof by Ski. By model theory of logic. And also, this and in the late 1990s, Bogomolov's conjecture has been proved by Ulmo. Well, the Bogomolov conjecture is more quantitative than the Manin-Drinfeld conjecture because it says that an actual inequality happens, and an explicit version of precise explicit version of Bogomolov's conjecture is due to David and Filippo. But don't ask me about the details. So Sinu is here. You can ask him. Filippo. And perhaps finally, so sometimes that the in simplified as process of conditions by Foster and Fink. And so so what is this for the background and about specifically modular curves, because the Manin-Drinfeld sense deals only with divisors supported on the cusp. But what happens actually if you take a divisor not supported on the cusp? And there is an explicit version of Manin-Drinfeld, which is due to Matt Baker. So this is not the Baker of linear form in logarithm. So it moved in the population of certain numbers, but very explicit way. My friends because they find it and take it actually. Distortion in Jacobian note is exactly the set of cusps. Well, there is provided if n prime, I think, greater than 71. So you can see that the cusps are really exceptional. If you take a divisor of this type, it cannot be torsion if P is not a cusp. Going back to the proof. That would be for term of n itself. So Manin-Drinfeld or why is that so? This is very simple. If you take so I said that a concurrent subgroup is it contains gamma of n, so for some n. So you can go from, so those are the divisors of degree 0 supported on the cusp. You have a surjective map. You can go to the Jacobian by taking the class. So if you have a divisor of degree 0 here, it lifts here. So therefore, it is torsion when you send it here, and therefore it is torsion when you send it. Very simple. Okay, so there is, so I'm going to describe the Manin-Drinfeld proof today or the next time, but there is an alternate proof. The case where I get a node of n for n prime, I can describe this quickly. N prime. You consider the famous delta function from Ramanujan. So delta of z is for q equal to pi I z. So this is a function on the upper half plane. And of course, it's well known this is a modular form. Of weight 12 for SL2 of z. And now you can consider delta of nz. This is a modular form, also of weight 12, but for the group gamma naught of n. It is very easy to see that there is this invariance by gamma naught of n, and you can take the ratio of the two, and the ratio of the two is of weight 0. And the important thing to note is that because it is a product, it does not vanish on the upper half plane. Is a function, so which is, if I write it correctly, this is n minus 1, sorry, product. This is capital N and N. To the power of 24. And so this function does not vanish and has no pole on the upper half plane. So this is a function on x gamma naught of n now. Think you take the ratio of two forms of the same weight, this is of weight 0. So this is a function on x without pole or 0. So the divisor has to be concentrated on the curve, and for the and this one set up only two elements share the class of people and the class of infinity. So the divisor of the function has to be concentrated on that, and it is with weight 0, so it cannot only be a multiple of the divisor 0 minus infinity, and you can find out easily what it is because the vanishing of this at okay, so if you let go z to I infinity, q goes to 0, so the function has a 0 at infinity, and it has to have a pole at the other cusp. So it has to be of divisor, I think it's n minus 1 times gamma naught of n infinity minus gamma naught of n 0. So obviously you have proved the Manin-Drinfeld theorem for the modular curve x naught of n, because any divisor of degree 0 has to be a multiple of the divisor, the cusp 0 minus the cusp infinity, and we have this divisor which is a divisor of a meromorphic function. So we are done. You have actually you can extend this method of proof to any congruent subgroup, but it's sort of complicated to make explicit the analog of those functions in general. Yeah, to cusp, and it's very easy to write the functions. So otherwise, you have to consider modular units. To see the general method, there is a certain reference for that, which is a book of generalization. To gamma of n. There is a book by Kubert and Lang called Modular Units. For all n. Well, I don't recall exactly. Well, I'm not 100% sure. In fact, maybe you are right. Maybe well, I think there are certainly in this book the tools to do it. Whether they'll do it explicitly for any n, I'm not. I believe so, but I'm not 100% sure. And so this alternate proof has the advantage of being explicit because it tells you exactly what is not only that the divisors are torsion, but also the order of torsion. So in particular, you know that the order of torsion has to be a divisor of n minus 1 for 0 minus infinity. It's not, in fact, n minus 1. It's a divisor of that. And the exact order in that case, I think, is the numerator of n minus 1 divided by 12. But the original Manin-Drinfeld proof is not explicit in that way. They have a way to show that the divisor is torsion, but you can put their proof into practice in every case. But there is no sort of general formula where this type of proof gives you a general formula. So there is also a more involved explicit question you must ask related to the Manin-Drinfeld theorem that I'm going to describe in a moment. So now let's turn to the tools of the tools actually to understand this question and to prove and to give the proof of Manin and Drinfeld. Yeah. So here is the analytic description of Jacobian. The complex point. Okay, so I'm just going to consider the complex point. So there is. Can be understood as a complex Lie group, where E is a complex vector space and L is a lattice. And L is a lattice. In the following way. Okay, so we have our Riemann surface and consider the global section of the holomorphic differential form on X gamma. And since is onto X gamma, let's call this map phi, you can pull back a differential form from X gamma to the upper half plane. And if you do that, you get certain differential form on the upper half plane. So, and you land on the space of modular forms of weight 2 for gamma. So modular forms, so in the following sense, so phi, I'm sorry, phi upper star of omega can be written as, so differential form of on the upper half plane. So let's call it f of v dz. Where if you write f slash gamma is equal to f, well, for gamma in the group gamma. So what do I mean by slash gamma? It is the fact that, so where for, let's say, gamma equal ABCD in GL2 of Q, f slash gamma is another function. So this is AD minus BC divided by CZ plus D squared times F of AZ plus B over CZ plus D. So S2 of gamma is a set of holomorphic functions on F on gamma such that F dash gamma is equal to gamma for all gamma in gamma. And also there is a condition at infinity. So F has to vanish when okay. So and F dash gamma of IY turn to 0 when y goes to infinity for all gamma in GL2 of Q. So this is a complete definition of the space of modular forms of weight 2 for gamma. So it's the same thing than actually the space of holomorphic differential form on X gamma. So now let's go back to the analytic description of the Jacobian. What is E and what is L? So E is a dual of the space of holomorphic differential form. And L is described as follows. Okay, I need to describe another group and consider the first homology group of the Jacobian, not of the Jacobian, of the curve itself, which you can see simply as a fundamental group, if you like, abelianized. Since you abelianize, there is the base point doesn't matter. I'm going to give an explicit description of this group in a moment, but for a while you can describe it topologically in this way. And there is a pairing between this group and the holomorphic differential form. So let L the image of the map to E, which to an homology class C associates the map, which to an holomorphic differential form associates the integral over C of omega. So you can integrate differential form over homology classes. If you see this homology group, so it's the same thing actually than if you take gamma. An explicit description is the following. If you take image, this is the image of the map which to gamma associates, which goes from gamma to E, which to a matrix gamma associates the map which to a modular form F associates the map from Z0 to gamma Z0 of F of Z dz. It's the same thing, and Z0 is any point in the upper half plane or even on P1 of Q. It doesn't matter. So that's another way of describing this L, and the theory tells you that L is actually a lattice in E. Of course, I know that many of you know already all that, but I think it's good to say things explicitly. Then, so L is a lattice. In J gamma, a lattice means it's a discrete co-compact subgroup of E. So if you like, so you can identify, if you like, J gamma with E model, which is the same thing that L tensor R mod C. So which is the same thing that H1 of X gamma Z, the description is H1 of X gamma Z tensor R mod Z, which is also, if you like, the homology with coefficients in R mod Z. There is an explicit description of this group that I mentioned. So this group is key actually to understand the Jacobian. But it can be embedded in a slightly larger group. So one has the long exact sequence. I'm sorry, it's still Z. So it can be embedded into larger homology group. Okay. Write a bit more compactly. Z. Okay, so this map is just a degree. And so I'm going to write down explicitly this group and this map, so you get a description of this group. So description. So this is a group generated by, the symbols, by the alpha beta, with alpha beta in P1 of Q, with the relations alpha beta plus beta gamma is equal to alpha gamma. That's the first relation. And also G alpha, G beta. So this is still the homographic action is equal to alpha beta for all G in gamma. And of course, alpha beta gamma belong to P1 of Q. So it's very simple description. And the map here is a map which to alpha beta associates obviously the class. So gamma beta is a cusp minus gamma alpha. And obviously it's of degree 0, so this is why you have to fall into the divisors of degree 0. Okay, and this homology group is just a kernel. So you have a complete description of these objects. Okay, so now let me write the fundamental diagram. So you've got yeah. Fundamental diagram. You can send this group into the dual of the differential forms or the dual of the modular forms in the following way. Which to alpha beta goes to E. And recall that well, it goes to E by the map which to a differential form or rather a modular form, if you like, which to F associates the integral from alpha to beta of f of z. So it's not an integral over a closed cycle because this cycle is not necessarily closed, but it's well defined. So that's one thing. And as I mentioned, there is this map toward the cuspidal divisors of degree 0. And also you can take the quotient of E by L and you get the Jacobian. And also you get this map which to a divisor associates its class to the Jacobian. And of course, there is a theorem which I think goes back to Abel in the early 19th century, which says that this is commutative. So this is how the algebraic description and the analytic description of the Jacobian come together. All right. But it means in particular that since E is L tensorized by R, and in fact E is this homology group tensorized by R, that there is a retraction now to this group tensorized by R. What time is it? Okay, so just 3 minutes now. So one has map. Towards E, which is isomorphic to the absolute homology group. For R, or if you prefer, X1 of X gamma R. You can extend the scalar actually, so and this goes into the divisors of degree 0 with real coefficients. So let's call this map R. So now the kernel of R is a set of Eisenstein classes by definition. And obviously, now if you take a divisor of degree 0, there will be only one Eisenstein classes who has the same divisor. So you have a section actually here for the in R. There exists a unique ED Eisenstein class such that the boundary, okay, I should give a name to this map. Let's call this D, and so this is also D by extension of scalars, such that D of ED is equal to D. And now, if you look at the fundamental diagram, what does it mean actually that D is torsion in the Jacobian? It means that the Eisenstein classes actually has rational coefficients. Okay, so I think it's a good time actually to stop. Before I stop, I shall say a few things. So this is actually what Manin-Drinfeld shows, that the Eisenstein class has rational coefficient. Now you have a question, which, of course, the denominator here of the Eisenstein class is exactly the order of the torsion point. But you can ask for more, actually. So what are the Eisenstein class? Okay, how can you write them down explicitly, especially since you have a very explicit description of those groups? Should be possible to write down the Eisenstein classes, and this has been done actually by various people, including me, actually, and there is myself, so explicit description of Eisenstein of ED. So in the congruent subgroup case, in that case, they are rational. By myself, Debargab Banerjee, Sri Lakshmi Krishnamurti, and a few years back by Banerjee and myself. So that's the concurrent subgroup case. As I tell you, it's a completely different theory than the non-concurrent subgroup case. And in the non-concurrent subgroup case, I did it recently with Debargaba energy. It's really transcendental. And I think we did it in some generality, and it will be the subject of my talk rather at the seminar level. So non-concurrent. But next time, I will give the proof of Manin-Drinfeld that these objects are torsion. And also, I'll try to give some perspective about the meaning of the Manin-Drinfeld theorem and also Baker's theorem, in fact. Okay, thank you very much.
Have any questions?
Yes.
Yeah, just a short compliment. There are so many proofs of Manin-Drinfeld, it's completely impossible to keep track of all of them. And I myself forget most of them. We discussed and forgot a few of them. But basically, there are, one more set of approach, because Bogomolov is also included more than long. So the Vojta Faltings approach also gives different proofs. So that gives you another family, and then both, and then again, these are included in the Zilberping conjectures, which means that in fact, if you can look at Shimura varieties approach, so Yafaev, Kigler, Wilmo, and others, that will also lead to proofs of Manin-Drinfeld, or at just the abelian variety case, and then you will have approaches by Bobiri, Massanzanier, Pilazanier, and others. So that gives you, and all these proofs also are.
Okay, this is exactly why actually I wanted to talk about the Manin-Drinfeld theorem, because there is all this direction toward arithmetic geometry, which is extremely rich, and also there is a connection with modular forms, which is also very rich. So it's really at the intersection of the two, which I find very satisfying.
I thought you also proved that the bad way that the cusps are actually